Hello and welcome to NPTEL MOOC on Fiber Optic Communication Systems and Techniques course. In the previous modules, we discussed slab waveguides and then we talked many times about something called as a mode. We talked about TE modes of different orders. We did not derive anything for those modes, or we did not derive any equation for TM modes, but we did talk about TM modes as well. So, we use this word mode repeatedly, and I promised you that the actual concept of a mode I will discuss it later, and in this class or in this module I would like to discuss what exactly do I mean by mode. Okay. So, this is something that must probably be familiar to you if in case you have studied electromagnetics and have dealt with waveguides. It is in that context that one normally talks about a mode, but I will briefly recapitulate that mode theory for you, so that we can understand what exactly are we talking about when we specify something as a mode, and then we talk about fiber modes in the later modules. Okay. So, let me introduce the concept of a mode by looking at a physical situation that is something very familiar to you. Okay. At least from your earlier studies, you should probably have seen this one many times, and even in our earlier modules we have actually dealt with this case, right. And that happens to be that of a simple metal, a perfectly electric conductor, for which metal is a very nice approximation, but just for mathematically being consistent I am going to consider this to be a perfect electric conductor, right. Now, you know that from boundary conditions that we discussed in one of the earlier modules, for this perfect electric conductor, and I am considering a dielectric medium. So, for example, this could be simple thing like air, okay, and we assume that this is a perfect lossless dielectric. We know that the tangential electric field component must be 0 at the PEC and dielectric, perfect dielectric boundary, correct. So, whatever the waves that may have been incident on this particular boundary, it is always necessary that the tangential component must go to 0. Of course, if I assume that the PEC is slightly thick, and then there is essentially no wave outside the PEC as well. So, essentially all of the electromagnetic wave that is incident onto this boundary would be reflected back, and you will not really find any field on the other side of the PEC boundary, right. So, that is something that we take it based on our experience of whatever that we have studied earlier, but the crucial condition that we are looking for is that the tangential component must be equal to 0. And because I am not specifying the nature of the electromagnetic wave, it does not mean that I am actually excluding light from this discussion. It is perfectly valid for us to include light as the wave, okay, because light is also an electromagnetic wave, and then incident light onto this perfect dielectric and PEC boundary. Okay. But normally metals are very lossy at optical frequencies, and therefore, their use as waveguides is not so much. Therefore, we do not really look at light, although technically it can be used to describe this modes, I mean describe this physical situation, or can be used in this physical situation. Okay. So, anyway, that was a small digression. So, let us come back to electromagnetic wave, perhaps at frequencies which are more suitable for sustaining these waveguide modes by metals, which happens to be a few gigahertz to tens of gigahertz, okay, or maybe hundreds of gigahertz. Anyway, so I have this perfect electric boundary. Now, let me put down some coordinate system to work with. So, let me say that this is x equal to 0 boundary, and of course, the parallel direction to the boundary that I am considering will be the z axis. Okay. So, my goal would be to kind of understand the wave propagation along the z axis, but I am going to see what exactly is going to happen when I send an electromagnetic wave at an angle, okay, which is say some angle theta I being the incident angle as measured with respect to the normal to the perfect electric conductor and the perfect dielectric boundary, which is located at x equal to 0. Okay. Now, when I send light in this way, you will immediately ask, this is not light, this is actually electromagnetic wave at a lower frequency. Okay. So, microwave field, for example. So, you will immediately ask whether I am considering a transverse electric polarized wave or a transverse magnetic polarized wave. To keep the math simple, Okay. I will assume that this is a transverse electric wave, which means that this would be the incident magnetic field, which anyway I am not going to look at it for now, but this would be the electric field incident, okay, which would be polarized along the y axis. Okay. So, electric field will be along the y axis. So, you can write down this incident electric field as we have written many times earlier as a function of both x and z, which has an amplitude of say Ey I, where Ey I is the amplitude of the electric field, which can be considered to be a constant, and of course, this wave is polarized along the y axis. So, this is the transverse electric polarization that I am actually considering. So, the incident wave is actually transverse electric polarized wave. So, anyway, so I know that this is essentially a plane wave that I have been considering. So, I will have the exponential or the phase factor of the form k I dot r, okay, where k I will be the incident wave vector, which itself has components along x and z. Clearly, this is given by k I, which is the magnitude of the incident wave vector, and the x component is given by x hat cos theta I plus, and the z component is given by z hat sin theta I, and I know that r position vector in this plane that I am considering is x hat plus z hat. So, if I can go back and substitute into this expression, I would have figured out everything that is needed to describe this physical scenario where the incident electric field is transverse electric polarized. Okay. Now, what happens at this boundary? Clearly, this boundary, at this boundary, the electromagnetic field would necessarily have a reflected field, correct. So, I will have a reflected field, which from Snell's law we know that makes the same angle theta I. So, where theta r is essentially equal to theta I. So, what changes here also we know, it is the reflected vector k r, which is in a direction that is different. So, it will still have a positive z component, but it will have a negative x component because it is moving away from the interface. So, the reflected field, if I were to write down, which would again be function of x and z, will still be polarized along y direction. I am assuming that the incident and reflected waves are both transverse electric polarized. Okay. This is slightly common sense, we do not expect the polarization to change once the wave actually is incident on the PEC and gets reflected from that one. Okay. Mathematically, of course, you can show that the reflected wave will also have the same polarization as the incident wave. Anyway, because the metal does not really do anything to that. So, you have ER as a function of x and z, which will have some amplitude, let us say EYR, okay, and then I will write down the full phase of expression out here. Instead of writing separately k r dot r, I will write down the expression because we have seen this many times. So, this would be minus k r cos theta I x plus k r sin theta I z. Of course, being the two mediums being the same for the incident and the reflected wave, I am just going to write this as k I equals k r, indicating that the magnitude of the reflected wave vector is the same as the magnitude of the incident wave vector. So, I have now a reflected electric field, I have a transmitted or rather incident electric field. Clearly, there is no transmitted electric field because this is a perfect electric conductor. So, there are no fields on the other side. Okay. So far, it seems that what we have done is very similar to a to a slab waveguide. In the slab waveguide analysis also we started out with a single boundary, right, and then we said that I am going to send in light at an angle which at that time would have to be greater than the critical angle, okay, and then the light would be reflected off. Only when there is a critical angle the light would be completely reflected off, there will be only evanescent fields on the other side, but the reflected field would then begin to propagate in the other direction. Okay. The polarizations would essentially remain the same. The only difference is that when it bounces off a dielectric medium, it acquires a phase shift which depends on whatever the polarization of the incident light is. So, if it was a transverse electric polarization, it would acquire phi TE as the phase shift upon reflection, or rather 2 phi TE upon as phase shift upon reflection, and if it was a transverse magnetic wave, it would have acquired 2 phi TM. But in the case of a perfect electric conductor, I mean wave impinging on a perfect electric conductor, the phase shift regardless of whether you are looking at TE or TM will be equal to 180 degrees. Okay. So, for that reason I could have equally worked with transverse magnetic polarized waves here, but that transverse magnetic polarization would also require me to decompose the electric field into two components. So, therefore, I have decided to avoid that slight mathematical extra hard work to simplify the work. I have chosen the transverse electric, but the ideas that I am talking about will apply equally to transverse magnetic fields as well. Okay. So, anyway, so I had this incident electric field, then there was a reflected electric field. The magnetic field will also have similar changes, but at this point I do not really need to know the magnetic field. Okay. So, the concept of a mode for the TE case can be explained only with the incident and reflected electric fields. Clearly, there is no transmitted electric field into the perfect electric conductor. So, all of the electromagnetic wave has actually reflected back. So, what is the total electric field in the first medium? In the first medium, the total electric field, which I will denote it as say E with a capital T, okay, or maybe if we want to specify more and not confuse ourselves with the transmitted field, I will write this as E with a subscript of TOT. Okay. So, this total electric field is given by, okay, so this total electric field is given by the sum of incident and reflected fields. Luckily for us, both are polarized in the same direction, and we will now write this as E by I e power minus j k I cos theta I x plus k I sin theta I z, okay, plus E y r. So, I am going to write a y hat outside here to indicate that this is actually the y directed field. So, I have E y r e power j k I cos theta I x minus k I sin theta I z. Okay. So, please note the signs that I have written, this is very crucial. And now, what is the condition? The condition that we were looking for is that at x equal to 0, the total electric field must be equal to 0. Actually, the tangential component of the total electric field must be equal to 0, but luckily for us the total electric field is already tangential because it is in the y direction. Therefore, we simply set this equation to 0. Okay. So, what I have, this will be 0 at x equal to 0. So, you can see the expression over here. When I put x equal to 0 in this one, this entire term will become 0. Okay. So, I do not need to consider that one, and what I have on the total the electric field is that the condition is that I have y hat E y I e to the power minus j, or rather since this e power minus j k I sin theta I will be a constant. So, I will have E y I plus E y r e to the power minus j k I sin theta I z. This will be equal to 0. So, this will actually be equal to 0 vector, but if you drop the vector thing, this will actually be equal to a 0, right. Clearly, this exponential term is not going to 0 because this expression has to be valid for whatever value of z that I take. So, there might be some values of z for which this exponential might be equal to 0, but if you move away from that z, then this exponential will not be equal to 0. So, the only conclusion that you can draw about this expression is that the reflected field amplitude must be equal to the incident field amplitude. So, once I know that the reflected field amplitude is equal to the incident field amplitude, now I can simplify the total electric field, which I am going to do now here. So, the total electric field that I have will be in the y direction. So, I am not going to indicate the direction of this one, simply write this as E total. This is in the first medium. Okay. So, this is important, this is in the first medium that I am considering. So, this will be equal to, you can show that this would be minus 2j E y I sin of k I cos theta I x, okay, times e power minus j k I sin theta I z. This is the phasor form of the electric field. If you were to write down the electric field as a function of z I mean the coordinates as well as time, what you get is 2 sin k I cos theta I x, there is no change with this one, but when you multiply this one by e power j omega t and then take the real part of it, what you get here is cos omega t minus k I sin theta I z minus pi by 2. So, forget about that initial phase pi by 2, if you forget about that one, that is not really important. What you have is a travelling wave. So, this is actually a travelling wave, but its amplitude also depends on x. So, there is some sort of a x dependence function and then there is a propagation term. In the phasor form this would be even better. So, in the phasor form this would be f of x e to the power minus j k z times z, where k z is my shorthand notation for writing k I sin theta I. Sometimes I will also write this as beta. So, I go back between k z and beta depending on the context or depending on the simplification that I would like to write. Okay. And this f of x will be function only of x coordinate value, right. In general, of course, it will be a function of both x and y coordinates, and then there will be along the z coordinate a factor which would account for a exponential phase, that is, this is actually the travelling wave, and whatever that you have is a function only of the transverse coordinates. Okay. And which transverse coordinates am I talking about? It is the transverse coordinates to the direction of propagation, right. So, I can write down my electric field in general, okay, whenever I am considering this type of problems. Okay, I should be able to write down this in the form of a product of two functions. One will be the function only of the transverse coordinates x and y, and the other one will correspond to the travelling wave part. Anyway, we will now discuss some very interesting features of this expression. So, please keep this expression in mind. Now, let us look at this expression. When I said interesting features, I mean only with, I mean with respect to x mainly. So, let us look at this expression. Clearly, when I set x equal to 0 in this expression, E total or electric field in the first medium will be equal to 0, right. Regardless of the value of z, at x equal to 0, this electric field will be equal to 0, and it will be equal to 0 simply because k I cos theta I times x will be 0. So, this entire thing is 0. So, sin of 0 is of course 0. Is there any other value of x for which this sine function becomes 0? Of course, yes. When the argument of sine function becomes pi, then that sine of pi will again be equal to 0, and the first time that it actually happens, right. So, you have k I have fixed k I, of course, because I have fixed the medium. I have fixed theta I because I have sent in a wave at a certain angle theta I, and as I vary x, by varying x means I am actually going down in this direction. So, this is my x equal to 0 boundary at which E total was actually equal to 0, but as I go along x at a certain value x equal to minus h, such that k I cos theta I h will be equal to some pi. Okay. The first time it happens it would be pi. At that point, because this electric field f of x function is actually sine of this argument here, and the argument going through pi means that that function f of x at x equal to, so at x equal to h, such that this condition is actually satisfied, will be equal to 0, right. So, at x equal to h, this would be x equal to h, the function again or the sine function goes to 0 and the electric field actually goes to 0. Okay. You can show that this continues again, and at x equal to 2h, or rather x equal to minus h and minus 2h. The reason I have put in a minus sign is because the fields are propagating in the negative x direction. So, except changing the sign of x, it does not really matter. So, you could equally have considered a wave initially in this direction, and then the wave would have bounced off. So, that could also have been done. So, this would have been x equal to 0 and this would have been the positive x direction. So, you could have done the same analysis with this coordinate system, but because I chose the other coordinate system, the values of x turn out to be minus h, minus 2h and so on. At these places, the electric field actually goes through 0. Okay. So, for example, this might be one such way in which the field could be distributed, that is, electric field E y is distributed in this particular manner, reaching a maxima at the center, and going through 0 at x equal to minus h, okay, if I restrict myself only to that. Of course, I could also have the the field extending beyond this value. Of course, it does extend beyond this value and goes through 0 at x equal to minus 2h and so on, right. So, at every multiple of h, this goes to 0. This is one possible solution, right, which satisfies the boundary condition that the field go through 0 at all these multiples. The other possible solution is that I actually have a double maxima here and then I have this type of a scenario. So, in terms of frequency, this is at a double frequency corresponding to this one, but this is also an equally valid solution, right. Of course, I do not have to restrict myself only to 2, I can have 3 maxima and so on and so forth. All these different field configurations where we have written this f of x, and remember f of x is actually the way in which the electric field component depends on x, right. So, I have fixed z, okay. Once I have fixed z, the dependence is essentially on x in the form of f of x, okay. So, this is e power minus j k z z, and this f of x can have multiple solutions, and all these solutions are equally valid, because in all those cases at x equal to minus h this would go to 0, at x equal to minus 2 h it would go to 0 and so on and so forth. Now, let me do one thing. I already know that I have a metal surface over here, right. So, this is a perfect electric conductor, which in fact allowed all these field quantities to actually start appearing, right. So, this is how the field looked, okay. So, the field is actually 0 at x equal to 0 and because of the perfect electric conductor. Now, what happens if I were to place another perfect electric conductor here? So, if I put another perfect electric conductor, these fields will not be sustained, okay. So, clearly these fields are gone because of the perfect electric conductor, and what I have actually achieved is a very interesting thing. I have achieved in terms of x, right, a function of x for a given constant value of z, but this pattern of half sinusoidal wave would actually move along the z axis. So, for example, if I go to another z axis, this would actually move, right, or this would be again in the same way, and this would keep on happening. So, what you actually have in this kind of a scenario where I have two perfect electric conductors, okay, with this kind of a boundary that I have. So, the pattern whatever that I have between the two perfect electric conducting walls is that this pattern, which is a function of x direction, which is this vertical direction that I am showing, and this pattern actually kind of moves along the z axis, and it is not just one particular pattern. So, it is not only one half sinusoidal cycle, it could be one complete sinusoidal cycle, it could be 3 sinusoidal half sinusoidal cycles, 4 half sinusoidal cycles, so on and so forth, and all these patterns are equally valid solutions for this problem that we have considered, okay. So, all that we did was to send in electromagnetic wave at an angle theta I, and what we managed to obtain is a functional dependence on x, which is a standing wave, and this standing wave will go to 0 at many places. But if I now were to place a perfect electric conductor at one of the places where the electric field is going to 0, then what I have done is to essentially bound my electromagnetic wave between the two walls, or bind the electromagnetic wave between the two walls, and this particular pattern, which is a function of x, would move along the direction z, indicating a travelling wave along the z. So, all that these two perfect electric conductors did was to establish the condition in such a way that they can guide the electromagnetic waves along the z axis. So, this is a very important thing, and you must have been familiar with this analysis. This is called as parallel plate waveguide, okay, sometimes also called as parallel plane waveguide, and these different patterns which are functions only of x in this particular case. So, this is a 2-dimensional parallel plate waveguide. You must also have studied a 3-dimensional rectangular waveguide, in which case the function, instead of being just a function of x, it would be a function of x and y, and these fields in general. So, I am writing only for the electric field, but magnetic field would also have the same kind of dependence. These fields in general are functions of transverse coordinates, okay. So, maybe I can write down in a general u v w coordinate system. So, these are functions of u and v, whereas along the w direction there will be a travelling wave. So, I have considered a general u, v and a w direction. So, this u and v are the plane that is here. This function f of u comma v will actually be a vector function, correct. So, this would be a vector function and this vector function is called as the mode. Okay. This vector function has to satisfy boundary conditions. So, f of x equal to 0 here, f of x equal to 0 at these two planes is actually the boundary condition. So, together with the boundary condition, this entire electric field is a solution of Maxwell's equation. Okay. So, any solution of Maxwell's equation together with the boundary conditions and the function which depends only on the transverse coordinates while being guided along the other coordinate which is perpendicular to these transverse coordinates is called a mode. Okay. So, a mode is nothing but a pattern of electric field and magnetic fields, okay, which satisfy boundary conditions, and of course, they are the solutions of wave equation, and these solutions are such that the overall electric field and magnetic field pattern can be written in the product form of a function that is dependent only on the transverse coordinates, and this transverse coordinate function is propagating along the other coordinate axis. Okay. So, in the case of a parallel plate waveguide, u was x, v was really not required for us because this was a one dimensional or a two dimensional parallel plate waveguide, and then w was equal to z. So, kw, which is the propagation constant, is actually equal to kz, right. And these patterns which I drew, as I told you, I can draw one pattern that way, I can also draw another pattern, right. So, this pattern would also be another mode, and then I can draw three patterns. These are all different modes of the waveguide. Okay. Turns out that the first waveguide mode is TE1, the next waveguide mode is TE2, then you have waveguide mode TE3 and so on. Okay. So, TE0 mode does not really exist, and these mode values that I am writing are simply the condition instead of k I cos theta I h being equal to pi, if this is equal to some nu pi, where nu is an integer. So, nu equal to 1, nu equal to 2, nu equal to 3, all these correspond to these different modes. One final point here before we complete this discussion. So far what I did was to consider this parallel plate waveguide, okay, and determine h according to the equation that I wrote. Okay, this is some sort of a transverse resonance condition, if you would remember it. So, according to this transverse resonance condition, what if I fix theta I, then h gets fixed. Okay. But it is possible for us to start off with a value of h here and then explore what possible theta I values are required to satisfy this equation. So, if I were to fix h, right, then not all theta I values are allowed, only certain theta I values are allowed which satisfy that resonance condition. K I cos theta I h must be equal to some integer multiple of pi. Okay. And this comes because I have fixed h, then it shows that not all values of theta I are possible, only those that are possible are given by the transverse resonance condition, and corresponding to different theta i's which are allowed solutions, you have a mode. So, corresponding to each theta I, you have a corresponding f of x function, and these are the correspondence between the angle of incidence and the modes. So, what we have discussed is the concept of a mode, which is a pattern of electric and magnetic fields. Okay. In the next module, we are going to look at how we can systematically analyze these waveguide structures. We are going to look at a systematic procedure to start from Maxwell's equation and end up having these modal solutions obtained. Thank you very much.